Okay, so hello everyone again and good afternoon. Welcome back to the second lecture scheduled today, where Christopher will tell us all about gravitational wave data analysis. So I think we have a quorum of online participants and the offline participants. So Christopher, the board is all yours. Do you want to take it away?
Cool. Thank you. Let me see if I can. Okay, so in the first couple of lectures, we have spoken about why compact binary coalescences are a good signal to look for, and highlighted some of the astrophysics of the sources. So what our different formation channels are. And hopefully you've come away from that convinced that these signals are worth looking for. So it's a good thing that we have this summer school to introduce you to them, but also with the idea that there's lots of complexities in the astrophysics, and there are lots of things that we don't know about these sources. So we do want to dive a bit deeper and understand these properties. And this is where observations come in useful, is to constrain our theories and tell us what nature really does. So moving on to the next couple of lectures, we're going to start talking about gravitational wave data analysis, how we go from the data from our detectors to an understanding of the source population. And so in the final lecture, we'll pull everything together and have a look at the latest results from Ligo and Virgo in this regard. Okay, so let's get started then. And here is my big picture overview of gravitational wave data analysis for Ligo, Virgo, and Kagura. And really what we're trying to do with our data analysis is answer a series of 3 questions. So the first is the detection problem of, is there a signal in our data? We have our stream of data coming in from our detector network. We want to search through this and find where there are gravitational wave signals. Starting off, this course was the big question of, can we see any gravitational waves? We can. Now this is something we know they exist, so it's just a question of where they are in the data and what they look like. So number 1, detection. Is there a signal in a particular stretch of data? Okay, so having established, yes, we think there is a signal, or at least there's a reasonable probability of there being a signal. The next question is, what are the properties of the signal? What does this tell us about the source? So this is what we often refer to as parameter estimation, or PE for short. So given our data, what can we infer about the source? This is where I spent a lot of my time over the last few years, is analyzing gravitational waves to infer their source properties. Now, the way we typically do this is on a signal by signal basis. So given this signal, what are the source parameters? So the final challenge is really, given the ensemble of observations, given the entire population, what can we learn about the underlying distribution of sources? So this is where we really start delving into the astrophysics. So hopefully from the previous lecture, you have an idea that there's a lot of overlap in the properties of different sources, so formed from different means. So overlapping masses, from a single spin observation, it can be difficult to tell whether you have one channel versus another, even if they have quite different predictions. We can have aligned spins formed dynamically, just as we could have anti-aligned, and if we see a misaligned spins, well, is that evidence of dynamical formation, or have we just seen a rare example of a system formed by isolated evolution which had some big supernova kicks to misalign things, for example? So most of the time we need to use the real power of the entire population to infer what's going on, and population inference is the name often given to this process of using the entire ensemble of observations to see what's going on. Now there's actually a link between tasks 1 and 3 here, that it's not strictly a case that we first say yes or no there's a signal, then we go what are the source properties, and then given the source properties, what are the properties of the underlying population. We actually have somewhat of a loop now in the way we do analysis, as the question of whether or not there is a signal is best answered when you have some idea of what the population is. So we'll come back to this in a little bit later, but when we're talking about a probability of astrophysical origin, often called P astro, this is saying what's the probability of there being a signal versus probability of not being a signal, and that to calculate relies on some knowledge of what the population of sources is like. So there's a bit of a loop to do things in a nice self-consistent way where we can infer the source population as well as looking at are there signals from a bunch of candidates. Okay, so in the course of this lecture, I'd like to give a brief overview of all of these different tasks: detection, parameter estimation, and population inference. Next time, we're going to go into more detail on population inferences. It's the task that's of most relevance for this course. So that's what we'll cover now. And here we'll only go into quite a high level. So there's a lot of extra things you can learn about these topics, but hopefully today we'll get a bit of an idea of the basics of these and you know, the ingredients of what more to study if you want to go into more depth. So let's start off with detection and the question of, is there a signal? We've spoken about the challenges of this a little bit in the first lecture. What we want to do is take some data, look at it and say, is there some extra signal in there? Given a knowledge of the noise distribution, this would be quite easy. If we only had nice Gaussian noise, this would be really easy, but we don't, we have extra things. So this makes things a bit challenged and we need to watch out for noise artifacts. So the best way we have currently of searching for signals is illustrated in this figure here. It's using a technique called matched filtering. And the idea here is that we search the data using templates. So if you know what you're looking for, it's easier to find what's going on. So in the top panel here, we have some strain data from our detectors, Hanford and Livingston here. This was during 01, so before Virgo came online, before we had Kagura in the network, so just the two detectors. And from this, just looking at the noisy data, you know, by eye, you would not necessarily be suspicious that there's any signal in this data at all, right? There's no pattern of wiggles that can be clearly identified because there's so much noise on top of it. However, we know what the signals should look like. We've seen the numerical relativity simulations, for example, that tell us what these look like. So we can have a template, we can sweep this through the data and see where it lines up. So in the plot below, well, let's take a second. This black line here is an example of a template. This is actually for 15, 12, 26. We saw the signal in the last lecture. It's a nice long in spiral for a binary black hole merger. We know what the signal should look like. We can overlay it, look for where it lines up. In the next panel down here, we have the accumulated signal to noise ratio. So as a function of time. So as we take this template, see what its overlap is with the data, we can see that, yep, the signal to noise ratio accumulates as we integrate up more and more time. This is why we like longer signals. We can match more and more cycles to see what's going on. And we end up here with signal to noise ratio of just under 10 in Hanford, a little bit lower, just under 8 or so in Livingston. So we have two peaks in our signal to noise ratio distribution as we integrate up with this template. Of course, we in general don't know where to look in our data, so we need to filter the data and pretty much continuously. The next plot here is showing that if we take the same template and try integrating at different time offsets, what we get. And you see, most of the time we get some SNR, right? There's noise fluctuations which will overlap with bits of the template, and these should give us a SNR distribution, plus or minus 1 or so for noise fluctuations. For Gaussian noise, and then we have this nice peak that clearly stands out from the background when we actually get to the time identified here. And this is how this candidate was identified. We look for peaks, two detectors at the same time, or within the light travel time window between the detectors, same template, looking up the same signal, that's a good indication of that we have something to see. Okay, so we have template, we look through it, and we can pick up what the signal looks like. The bottom panel here shows the time and frequency evolution of the data. For a gravitational wave signal from a compact binary coalescence, we expect something that starts at low frequency as the system, the two black holes, or neutron black hole, two black holes in this case, are far apart, they inspiral together, they get closer together, orbital frequency goes up until they plunge in together to merge, get the peak frequency, get quiet, ring down at the end here. So we'd expect to sweep in chirp up through here. And you can kind of pick out here these sort of yellow green areas, which can just about be a chirp. If you're looking at through either, this little bit of here is probably part of it. But it would be very tough to convince yourself by eye just looking at this that this was anything significant and not just a noise fluctuation. So it's really knowing what to look for and having the template that really helps with this. So this is the basic idea of match filtering. We have a template, we search through the data, we look for where it matches, and we can get extra confidence from the fact that we see the same signal in multiple detectors. Okay, now we can't just have one template for this, but we have many templates. We have a template bank covering the range of parameter space that we look for, and we see what's coming through here. The density of the template bank is something that needs to be carefully optimized to balance the having no gaps, so we don't have signals being missed because we don't have templates that align well enough to match, versus that if we have them too dense, well, that adds first to computational expense, but also more importantly, the more things we try, the more likely we are to get a noise fluctuation that matches something just by chance. So we have the more things we try, the higher the false alarm rate is just by chance. So you need to sort of balance the trials factor from trying many things versus the risk of potentially missing something. Okay, so we have so I've been told my video's freezing for a second. Did I skip out on something that I was saying?
No, your audio is quite clear, as is the annotations on the slides.
Okay, cool. Thank
Video
you.
just like last time, so I think that's fine.
Cool. Okay, it doesn't really matter what I look like, so slides are important. But okay, so template bank, search through the data, matched filtering. We look for signal to noise ratio by integrating up our template, which we know what it looks like. Okay, now if we had nice Gaussian noise, we could quite easily calculate the probability of getting a noise fluctuation by this by chance. However, we don't have nice Gaussian noise. We know there are large fluctuations in our data due to things like glitches and other harder to identify noise fluctuations that can cause us problems. And you can imagine, say, if we just had a really loud spike in the data, say at this point with the template, when we would take the overlap between the template and the data, we could potentially get a very large value because there's a large overlap at that particular point, even though the rest of the signal doesn't match. So it's not enough just to look at signal to noise ratio, just to look at the overlap between the signal and the data. We need to also consider the consistency of the template over its entire frequency evolution. So typically we have a search algorithm that considers both the signal to noise ratio, the total output of this, and also some kind of consistency test, breaking up the template into different bits, maybe in frequency, and seeing how those are consistent with each other. Do we have the right amount of power being balanced in each approach? Okay. Then we have some mapping now between our signal to noise ratio distribution and our consistency test. We combine those in some way to form a ranking statistic. So the idea here is we have some measure of how significant a candidate is. We assign this to each candidate a ranking statistic, and then we evaluate the significance of this by comparing to background data. Okay, so what we have in this slide is results from our first searches for gravitational wave signals at the end of our first observing a run with advanced Ligo. And we have a couple of plots here. Let's just take a look at the top plot for now. We have the results from two search algorithms. The one on the left is PyCBC. The one on the right is GST-LAO. These are both two algorithms that use templates to search for gravitational waves from compact binary coalescences. There are various differences in their implementation. And they have two different ranking statistics that calculate similar things in different ways. They're both a combination of the signal-to-noise ratio and a measure of consistency. For PyCBC, it adds a weighting to the signal-to-noise ratio based on the consistency of different segments. It's a very nice paper by Bruce Allen which explains the background of this. It's very readable if you want to know a bit more about this. Okay. And it constructs a ranking statistic which is something like signal-to-noise ratio, but not exactly signal-to-noise ratio. And over here is a log likelihood for GST-LAO. This is constructed by sort of making a 2D histogram of the distribution of consistency statistic and signal-to-noise ratio, and from that inferring the properties of the signal. So similar ingredients combined in different ways. In both cases, we make a distribution of these ranking statistics. We put things in order. And the larger the ranking statistic, the more signal-like something is saying. It is. And what we do is we assume, okay, if we only had noise, what is the probability of getting this ranking statistic? So what we do is we calculate a background that contains no real signals and see what the distribution of the ranking statistic is like. If we just had pure Gaussian noise, we could do this analytically just using signal-to-noise ratio. Because we don't know the mathematical properties of the noise distribution, we have to construct this background empirically. So this is often done via a technique such as time slide, where we use the data from our alternative detectors, but we slide them in time such that there's no possibility of a real signal appearing in both data streams at the same time, because we've slid them past each other by an interval much greater than the light travel time. So there could be no real physical signal, and any coincidence between the two detectors is just by chance. Okay, that's done for PyCBC. GST-LAO does something slightly different with some cumulative distributions and extrapolation, but the idea is still building up a background of what the distribution of ranking statistics looks like in the absence of signals. Okay, so in these plots, we have the background distribution plotted in black here. Okay, and you can see, okay, there's a nice tail of the distribution down to going down. So we have more things with low ranking statistics. That makes sense. We don't expect these to be more common, and as the ranking statistic gets larger, these should be rarer. These should be more signal-like things. These should stand out from the background. These become rarer. But we have this long tail, which is basically we expect somewhat as these are the non-Gaussian features. Okay, so this is our search background, and the search result, so the actual real data from our detectors, is here shown in orange. And you can see the distribution of events is well above the background. Now, the further away you are from the background, so at a given ranking statistic, obviously, further away you are from the cumulative distribution, the more significant you are. So this is how we can identify 150914, is it's a clear outlier from our search background. So this is extremely significant. We'll come back to exactly what this means in a second, but extremely significant. And this is how we've identified our first gravitational wave. Now, there's a slight complication of if we have an empirically determined background and we've included a real signal in that, then we're potentially polluting our background. As when we calculate our background, we could be time sliding some noise fluctuation, so it overlaps the real signal in the detector, and we'd expect that to have a larger detection statistic than if there were no signal in the data, because it's really the real signal is boosting the detection session. So what we could do is we can subtract out the real signal. So having identified the real signal, let's just zero out that little bit of data and then repeat our search results. And then we get this new background that's shown in purple, so excluding this here. So when you do this, this tail just drops off. You can see that it's not just the 5914, which is a clear outlier, but we have sort of other outliers here, which become much more significant. As you see, the drop between the background and the becomes much greater as we take this out. And this is here 15, 12, 26. So here in the second panel is just to zoom in to look at this and repeating the process of subtracting out 15, 12, 26 from the background estimate. And you see each time we do this, we become sort of a smoother and smoother distribution of background, which is what we'd expect when we take out the signals here. And this is this next candidate here would be 15, 10, 12 from the background. So you can see this is closer. It's lower significance. In later analyses, when we've changed up our algorithm slightly, adding in some extra requirements on what the signal should look like, that boosted this significance, so we became more confident of it. But even from this first analysis, you can see it's standing out from the background. Okay, so come back. How do we calculate? How do we identify potential signals in our data? Well, we construct a ranking statistic based on the fact that we know what we're looking for. We know what the signal to noise ratio. We know what the signals should look like, so we can calculate signal to noise ratio. We can look for consistency. We combine consistency check, signal to noise ratio, concoct some ranking statistic, which is some mapping of these parameters to give us a number. We can construct an empirical distribution of what this detection statistic should look like if we only had noise in our detectors, and then we can see, are there any outliers in this? From this, we calculate a false alarm rate. Okay, so what the false alarm rate is what is often quoted on this. So far, how it's often denoted. Okay, this is the rate of candidate with ranking statistics. Let's use the row hat of PyCBC just as a standard. So we want that at least as high as whatever is observed. Okay, when only noise. So given the hypothesis that there's only noise in our detectors, how frequently would we get a ranking statistic equal to or higher than the one observed, given that there's just noise in our detectors? And this is what the false alarm rate is. This is what the significance of the events is often associated with. So a smaller FAR, a smaller false alarm rate, meaning that the rate is lower, means a higher significance. So something, say, false alarm rate of 1 per century means we would have to observe for, say, 100 years to see something like this would be highly significant. So that's what the false alarm rate is. Okay, so this is the primary way we identify candidates. Coming back to what we were discussing a little bit earlier about, we don't only want to use false alarm rate for establishing significance, we also want P-astro, which is quite commonly used, which is the probability of astrophysical origin. Now, the false alarm rate is not exactly the thing we want to use to establish whether or not we have a real signal, because the false alarm rate is the rate of getting a candidate with this ranking statistic when we assume there is only noise. In the false alarm rate calculation, all we are doing is using the properties of the noise distribution of our detector. We are not considering what is the probability of it being a true signal. Okay, so what P-astro is it is the true alarm rate divided by the true alarm rate plus the false alarm rate. Okay. The true alarm rate is the rate of getting a candidate with a ranking statistic greater than the same threshold when that actually, from an actual signal. So you can see when the true alarm rate is higher, we're more likely to have a true signal. P astro is larger. If the true alarm rate and the false alarm rate are equal, then we have about equal odds of it being real or false. So if we had a candidate that the false alarm rate was once per 10 years, okay, we expect to see one every 10 years or so. And if the type of signal it is a signal which we think, oh, that should only happen once every 10 years or so, where do you put your money? Well, it's equally probable that it's a false alarm rate, sorry, false alarm, random noise fluctuation, rare admittedly, but equally the alternative is it's a rare type of signal. So P astro is really the best way of encoding all our knowledge, not just of the noise distribution, but also of the signal distribution in order to establish candidates. So P astro is the thing which is really best for selecting candidates. The problem is we don't know what the true alarm rate is. We can construct the false alarm rate from looking at our detectors, but the true alarm rate depends on the source population. Okay, so you can imagine, if you've not seen a particular type of signal before, you don't know how many there should be, how common it is. If there are no black holes, say, with a mass of 2 solar masses, and we saw a signal which was consistent with having a 2 solar mass object, well then the true alarm rate should be 0. Right? We should never see these. So even if it had a really good false alarm rate, we would have to conclude that it was a false alarm. So we don't know this going in, so we really have to do this self-consistently. At the same time, try and work out the false alarm rate, the true alarm rate, probability of astrophysical knowledge. So it's quite difficult to do everything all together. Okay, so detection is what we're really interested in for this first challenge. Okay, we have a way of calculating false alarm rate. We're interested in calculating P astro to know if we really have a candidate. We have some idea that we need to try and infer the source distribution. This is where the population inference will come in a bit later. Okay, just to come back, take a quick look at some exciting things about the aforementioned noise bursts. Here's a very famous example of a glitch that happened at the time of GW 170817, which was our first observation of a binary neutron star. Here you can make out it's a beautiful chirp sweeping up in frequency. It's a very loud signal through time and frequency, and you can see that this is completely overshadowed by this loud burst of noise, which is the glitch here. So when we saw the signal, actually, we didn't immediately know it was a detection because this polluted the data from Livingston. We were just going off Hanford to see there was something in. So we had, taking a quick look at this, it was quite easy to see that there indeed was something, and we could subtract out the glitch and claim that we had seen something. But then the next stage of inferring the source parameters proved to be very problematic because of the assumptions that the noise is Gaussian for that. So we had to invent some ways to get around this very quickly because we wanted to know the source position, so the sky localization, very quickly, so we could tell astronomers about this and where to look. So this turned out to be a big problem. So I want to stress that glitches not just something that pollute our background and make detection harder, but they can also overlap signals. So even if we can distinguish them and make the detection, they do impact the next step of parameter estimation as well. So this is sort of an ongoing thing of best how to understand to improve our data here. There's a whole range of different glitches out there. Some of them can be extremely loud indeed, and so loud, in fact, that they can cause drops in the detector performance. There's a whole host of different causes of them, some environmental, some instrumental, many we don't quite know the origins of yet. So whenever talking about the performance of a detector, one should not only care about the strain sensitivity, so the average noise performance, one should take keen interest in the data quality, the frequency of glitches and things like this. Okay, so let's assume we can do detection, even with complicated things like glitches. Let's move on now to think a bit more about the next stage of parameter estimation. So we saw these three signals in the last lecture, talking about how we can go from the signal to the source properties. We talked about how we have different lengths of the signal, so merging at different frequencies, and how this should be related to the total mass of the system.
Excuse me.
Higher masses, bigger black holes should correspond to lower frequencies because they're still further apart when they merge. So we would expect 150914.
There's
Yes.
a couple of questions here.
Oh, okay.
In the previous slide, you have a gray colored curve in the strain time, I mean the time series. Is that a window?
Yes, good
Okay.
question and well observed. Yes, so this was a window that was applied for some of the early detection to zero out the glitch. So this is good enough for convincing us I had a signal. It was not quite good enough for the parameter estimation. So when you do some weird things to this data, that can bias you. So this actually we ended up subtracting out. So this panel down here has a glitch model. So we did an analysis which tried to model the glitch with a series of wavelets and subtracted that out, and then we analyzed the residuals when we came to do parameter estimation.
Oh, thank you.
Hi, I had a clarification about false alarm rate. So when we say false alarm rate, do we also take the trials factor into account? Because I had to deal with it once. So I don't know if when we say false alarm rate, do we also take the number of templates we're using to search for the signal into account?
Yeah, another good question. So when we say false alarm rate in our Ligo, Virgo, Kagura analyses, yes, we include the trials factor from the number of templates used and things like that in our analyses. So the false alarm rate is the overall false alarm rate for the analysis, not just the false alarm rate for the signal. Okay, there are some other analyses you'll see in the literature where maybe they don't quite do it as comprehensively as that. They do it per subset of template bank or something like that. So that can sometimes give you a factor of a few. What is not done in our Ligo, Virgo, Kagura analysis yet is an overall trials factor from the fact we are doing many different search analyses. So the fact that we are doing GSTLAL and PyCBC and another version of PyCBC and MBTA and maybe SPEAR or something, all these other analyses. So there should be if we wanted to quote one overall false alarm rate, then we should put in a trials factor. We don't do that. We just quote trials factor per analyses. And that's because calculating a trials factor between pipelines is quite involved. And to think about this, it's handy to think about, take a step back for a second. So one might naively think, okay, if we're doing two search analyses, the trials factor should be 2. So we get, a false alarm rate that's twice as large as it would be otherwise. However, that only works if we're doing things which are really completely independent. And so as a way of imagining this, imagine that I took the code for PyCBC, I copied and pasted it and called it PyCBC2, and I ran that in exactly the same configuration. I'm going to get exactly the same search results out. Okay, so I haven't actually, I've done 2 search analyses, but I shouldn't increase my trials factor because the search results are perfectly correlated. There's no trials factor associated with that. The false alarm rate should be the same. When we have, say, GSTLAL and PyCBC, they're not exactly the same codes. So it's, we don't expect exactly the same search results, but they're very similar codes. They're sensitive to the same sorts of signals. There are some similarities in the way they rank statistics. So while they're not identical, they're very similar. So the trials factor would effectively be some number between 1 and 2. Okay, and actually calculating what that is quite difficult. So we generally don't get into those complexities and just say, okay, PyCBC had this, GST-Lab had that, and you can make your own adjustment for those going forwards, but we'll just leave it at that stage. Does that all make sense?
Yeah, it does. Just one more doubt. So this calculating trials factor across different searches is difficult. But when we talk about one search, is it just the number of templates used, or do you also look for whether the different templates for different parameters are independent or not?
Yeah, so I believe the way it's normally done is via a binning up. So it sort of takes into account some correlations between templates. But I'm afraid I'm not enough expert into the specifics of how the additional, each individual algorithm works to tell you exactly how that's calculated.
Thanks.
If you do want to look into this a bit more, you can of course find the papers. This paper here is a good introduction to the algorithms used in O1. They have advanced somewhat from that. If you look at any catalog paper, it will have links to the individual methods papers, the different search analyses in, so you can take a look in and try and dig into exactly how these things are calculated for each of the different pipelines. Okay, well, yes, so let's say we have a signal. Let's then move on to look at the source parameters. We were talking about how we could have total mass inferred from looking at the signal, but there's more information from this. I think we already touched on the fact that if we're further away, then the signal should be quieter. Since we know what the amplitude is from the masses, that gives us the distance. It's not quite as simple as that though, as the amplitude of the signal also depends on the orientation of the binary. So if we're looking at the binary from the side, what's called edge on, that should be quieter than if we're looking down or up on it, and that would, which we call face on or face off. The signal should be louder there. So we have a degeneracy between the inclination of the binary and the distance. Of both of those control the amplitude. Amplitude seen in each individual detector also depends on the position on the sky. The detectors are most sensitive to sources from above and below. So there's some degeneracy between amplitude, position on the sky. However, we can use the time delays and the phases seen at the different detectors to also constrain the position on the sky. So source direction comes in there, amplitude as well. We have the total mass setting the merger. The rate at which we inspiral is set by the chirp mass, a particular combination of the two components that we mentioned in the last lecture. And the longer the inspiral we have, the better we're going to measure the chirp mass. So the accuracy at which we can measure things also depends on the type of signal. When we have a high mass signal, we have lots of merge and ring down. We can measure the total mass better. When we have a lighter signal, lots of inspiral, we measure the chirp mass better. The spins put some quite subtle effects on this. So after chirp mass to next order, it's the mass ratio and the aligned spins that really give the rate of inspiral. So we can chi-effective combination of mass weighted combination of the spins parallel to the orbital angular momentum that we also mentioned last lecture. We can get some information about that from the inspiral, and it's also related to the final spin of the black hole, which controls the ring down, so we can get some extra information from that. But it is degenerate with the mass ratio to some extent, and potentially the in-plane components of the spin, so the one parts of the spin which are not aligned but in the orbital plane, go into precession, which gives some extra modulation to this inspiral here. So we can match templates to our data. We can see how well they fit. Because we know there is noise, there's some kind of jitter that we can associate with these. So we can calculate what's the probability of the noise fluctuation that we need to add to this template in order to match our data. Some noise realizations are more probable than others. And so using this, we can map out the probability distribution for the source parameters. So here we have probability distributions on the two component masses for these three signals from our first observing one that I just showed. These contours show 50 and 90% credible intervals. So there's a 50% probability of being inside the inner contour and 90% inside the outer contour, given our assumptions about what's about the source parameters and our assumptions that the noise is nice and Gaussian. So this is why it's important to subtract out any glitches, because that would violate that assumption. So you can see 150914 is much more massive, around about 30 solar masses or so. You can see you have a degeneracy in that we could have a larger M1 if we have a smaller M2. It's because we can measure the total mass quite well because we get the motion ring down. If we were looking at 151226, we see we have a degeneracy along this banana curve, and this is basically a line of constant chirp mass. So we measure the chirp mass quite well because there's lots of in spiral. So we know what the chirp mass is, but we're not so certain of what the mass ratio is, so we're not quite as certain as what's going on here. Near equal mass, a line of constant chirp mass is roughly equal to a line of constant total mass. So actually the constraints on the in spiral of 150914 also give us the same shape degeneracy just along this line here. Okay. So line of constant chirp mass gives us this degeneracy here. Looking at LV 151012, later known as GW 151012. See, this also follows this line of constant chirp mass, but here the uncertainties are much larger. And this is because this is a quieter signal, larger signal to noise ratio, lower signal to noise ratio, so larger statistical uncertainties. The higher the signal to noise ratio, the smaller the uncertainties are. Since this is a quiet signal, there's less that we can tell about what's going on, so we have wider confidence. Okay, so we can understand the shape of these from the form of the signals. What is really going on here, as I said, is an example of some inference. So what we are doing, okay, wrong window. Here we go. Okay, is a particular example of some Bayesian inference in this case. So from basic probability, hopefully people have seen this type of thing before, probability of A given B, okay, is equal to the probability of B given A times the probability of A divided by the probability of B. Is that familiar to people? If I write that type of thing, we can take a moment to go through it if this is something unfamiliar. Okay, I'm only hearing silence, which means I don't know what's going on. So I'm going to guess everyone's too shy to say either that this is something they're desperately familiar with, so they don't need to hear again, or they've never seen it before, so they'd really like to go through it. So let's err on the side of caution and just take a moment to go through this again. So this is the result we're going to use. This is Bayes' theorem. Okay, and it's actually nothing too complicated. If we start with a probability of both A and B being true, this is equal to the probability of A being true, and then the probability of B given A is true. So first have A happening, then have B happening given that A happening. This is also equal to, we could just flip the order, probability of B happening, and then the probability of A happening given that B has already happened. Okay. So probability of both A and B being true, probability of A being true, then the probability of B being true given A is true, or equally the other way around. Given this, we can rearrange. If we want to write it this way, we can take this probability of A given B is equal probability of A times probability of B given A divided by the probability of B. So let's write this in the same order. Probability of B given A, probability of A, or divided by probability of B. So this just relates some conditional probabilities to each other. This is always true. This is just mathematics of probability. Now, when it comes to doing some inference, we're going to apply Bayes' theorem to the particular case that we're interested in. So what we have is we have some data. Let's call this D. So we want the probability distribution describing the source parameters, which I'll call theta, of our source. So theta would include the masses, the spins, and a whole bunch of other things. Altogether, that goes into theta. And so we want the probability distribution over these given the data, right? We know we have the data, so that's what we want to do. So the way to calculate this, just writing this in, probability of the data given theta times probability of theta before we had the data divided by the probability of the data. And within Bayesian inference, these different terms have different names. So this term here is the posterior, because this is what we get out the back. This is the thing at the end of the calculation. This term here, what we are assuming about the source parameters before we observe them, is called the prior. That encodes our prior knowledge. Okay. This term here, the probability of getting the data given the source parameters, is called the likelihood. This is the thing where we often put most of our time and effort into calculating. And this thing on the bottom is sometimes called the marginalized likelihood, because we can calculate it by integrating up the likelihood, what's otherwise known as the evidence. And this is particularly important when we come through to calculate probabilities of different models when we're doing population inference. So we can calculate this evidence, marginalized likelihood, as this is just equal to the integral of our likelihood times our prior, integrating over all possible values of our source parameters. So we can calculate this using an integral to calculate it up. Numerically, this is often very expensive to calculate, but there are various algorithms like nested sampling that can calculate this efficiently. Okay, so evidence, often calculated here. If we only care about the shape of the distributions, we'll often not worry about calculating this, as it's just a normalization constant, so we just care about the distribution. Other components, the prior, this we will see is very important. This is what we want to assume about these parameters going in. Now, in our analyses within Ligo, Virgo, and Kagura, we try and assume an uninformative prior. So something that's not going to put tight constraints on any of the individual parameters. This is not necessarily the most physical assumption to make. Right? We could equally well have an assumption that says, okay, from our understanding of supernova explosions, we don't expect there to be any masses above the pair instability supernova. We could put in a prior on our masses that encodes that. Problem is that, of course, then given that, we're never going to get any evidence for being in that gap, because we're never going to allow ourselves to go into that gap. So we like to be a bit more agnostic and say we take a uniform distribution over our component masses, isotopic distribution of spin, so we can get anything. And we'll come back to talk about this a little bit later, why that is a sensible choice for people to then take our results and do their own analysis going forward. Okay, so we have our prior, which encodes what we know before. Generally, we try and put something uninformative in, but this will be important when we come to interpret our results. And we know we can calculate the evidence via this integral. The term we're missing now is the likelihood, which appears both here and here. This is the probability of getting the data if we had these source parameters. And this we calculate from our understanding of the noise in our detectors. Basically, the probability of getting a particular bit of data given our source parameters. Okay, what do we do to calculate this? Well, we assume that our data is made up of some signal plus some noise at a particular time. So what's the probability of getting this particular bit of data given our signal? Well, it's the same as the probability of getting this particular noise realization. Okay. What's the probability of getting this particular noise realization? Well, we calculate this from the assumption that we have Gaussian noise. You remember, we characterize our noise properties with a noise curve. It looks something like this. And this says that at any particular frequency, we expect that our noise is zero mean and has a variance given by the paraspectral density, this noise curve here. So our probability of getting noise at a given frequency, okay, probability of getting noise at a particular frequency, let's call that n dot I to denote it's at some frequency fi, is just going to be a Gaussian with zero mean, not the probability of so getting this zero mean, but a variance set by the this here at this particular noise frequency. So we're going to have something which is a Gaussian, so something exponential times the amplitude at that particular frequency, whatever that is, squared divided by s of n at fi. It's going to be something like that. So zero mean Gaussian with a variance set by this particular frequency. So far happy with that? Just a Gaussian distribution of a given frequency. We have now, of course, this noise at many different frequencies. So we calculate the probability of noise at the next frequency, ij, multiply it by this one, multiply it by next one. You end up with a whole bunch of Gaussians multiplied together. Can just, when you multiply Gaussians together, of course, you could just equally add the sums. So the overall probability of the noise is just a sum over of getting all the noise fluctuations for the different frequency bands. So it's a big fancy Gaussian is our likelihood. Okay, so we calculate our big fancy Gaussian. We take our data, subtract our signal template from it to calculate the noise, weight it by the paraspectral density. That gives us a likelihood. Plug this in to this calculation up here, multiply by the prior. We map out this probability distribution. In practice, this is very expensive because calculating the signal requires a particular model. We need to calculate this for the parameters, and that is quite expensive. So if we were doing this with numerical relativity, it would be infeasible, as we need to calculate many templates, each one of which takes a huge number of CPU hours to calculate. So we can't do that, so we use approximate methods. We use PN approaches, effective one-body templates, phenomenological models calibrated to these to calculate these. We map out the probability distribution, calculating this repeatedly, so we can calculate the probability of each set of parameters, and that's what we get at the end. Okay, I'm going to pause for a second as see if there's some questions on this. I've not seen any that perhaps suggests people need a second to absorb this. Okay, what does P of D denote? So this is the evidence term. This is the probability of getting this particular realization of the data. So we can understand this a bit more by this integral here. So let's look at what each one of these terms means. Okay, so probability. So let's assume we knew we had a particular set of source parameters, theta. What is the probability of getting that particular realization of the data? We can calculate that from the likelihood, right? So we know we have this signal. What's the probability of getting this data? Probability of getting the right bit of noise to get things to match up. So if we had this value of theta, we could calculate the probability of getting this data. We don't know, however, for this calculation, what the value of theta is. So we want to weight this by, okay, what was the probability of having that value of theta? So we multiply probability of getting that data given that value of theta by the probability of having that value of theta. Okay. That's the probability of getting this particular realization of the data. And then we need to consider all possible values of theta, all possible values of source parameters. So we do the integral over the entirety of parameter space to get the properties of this. So this is the probability of having this particular realization of the data given our prior assumptions. Does that make sense? This often takes the most thought to try and get your head around. As, of course, we know we have this data, right? It's sitting on our hard disks. We know that it did exist, but we need to calculate it for the normalization purposes. Given what we knew going in, what was the probability of getting this data? Okay, so this is what we do in parameter estimation. Really just calculating some Gaussians and exploring things, but there are lots of complicated bits of analysis that need to go into this. Happy to answer some more questions on some of the technical aspects of this and complexities of real data if we like, but remembering that we want to try and keep things relatively high level so we can get through the big picture. I think this will be enough for now. And the main thing to take away is that this depends on our signal model and it depends on our prior assumptions, as both of these will come up when we come to talk about the results going on. Okay, so let's move back. Oh, sorry,
no.
Go ahead.
Yeah, my question is that P of different parameters is equal to P noise. I still did not understand that very well.
Okay, so let me skip back for a second. Wrong window. Okay. Yeah, so you're confused about this statement here.
Right, yeah.
Okay, so this is just saying what we are assuming is our data is made up of a signal and a particular noise realization. Okay. So given the value of theta, we know what the signal is, right? So we know what this part is. So the probability of getting this particular realization of the data is just the probability of getting the right realization of the noise. So let's just rewrite this. Noise equals data minus the signal. Okay, so what's the probability of getting the data given theta? Well, given theta, we know what S is, so the probability of getting this D is just the same, the probability of getting this particular realization of the noise.
Okay, yeah, thank you.
Let's just take a second to write this, sketch out something for that. Okay, so what we're saying is that our data is made up of some signal. Okay, given the parameters, we know exactly what that is like. We know our data instead looks like something like this. Okay, so we know that we need some noise, which is the difference between these, that we add together. So when we add that onto the signal, we get the noise out the front. So you subtract those out, you get the noise residuals, whatever those look like. And we want to calculate the probability of getting this particular noise realization. If we were to pick a different template, so if we consider a different point in parameter space, this red curve will change while green changes the same, which means the noise we need to get out the end will change. And so it may become more or less probable depending on the particular noise fluctuation that we need.
Okay, thank you.
So it really just comes down to understanding our noise properties. Fine if it's Gaussian, which is a reasonable assumption over short timescales much of the time. but not if we have a glitch in there. And this is in fact why improving the sensitivity of our detectors can make analysis more difficult. As when we increase the sensitivity of our detectors, we can see signals for longer. We can see them down to lower frequencies, longer in spiral time. The longer the signal is, the greater the probability of intersecting a glitch and ruining our assumptions of nice Gaussian noise. Okay. So let's try moving on again. So source parameters here, these are probability contours, mapping out our posterior probability distribution on our two sources, source masses M1 and M2. And I should add, this gray region up here is just showing the region of parameter space which can't be occupied by convention. By convention, we always take M1 to be greater than M2, so it can never be in this gray region, which is where it's shaded. Okay, now the form of these contours given by our posterior probability distribution does depend on our prior assumptions. So if we used a different prior distribution, these contours would shift around. That is correct. That is why we need to bear in mind what our priors are when making interpretation. Okay, so we've measured our individual source parameters. What do we do next? This is the population inference. So what I'm showing in this result is the inferred mass distribution for primary masses given our most recent catalogue of observations, GWTC3. Okay, so the way we calculate this is we look at all the observations we have, all the masses that we have from our observation, and then we need to correct for selection effects. Now, our searches are not equally sensitive to all potential binaries. There are two reasons for this. One is the intrinsic noise properties of our detectors. So the fact that we can only see over a particular frequency range means we can only pick up certain signals. Some signals, if we go back here, will be louder because they have more power in the range of the detectors that we're sensitive. So this is our noise curve. So if we have lots of signal when we're above the noise curve, that equals high signal to noise ratio. So we have a signal that has lots of power in the region where we're sensitive, that's going to be high signal to noise ratio. If it's only lower frequencies, say, or if most of the power is at high frequencies where the noise curve is high, that would be quieter. So we have different sensitivity due to the noise properties of our detector to different systems. And also we have different efficiency of our detection pipelines to different regions of parameter space. So this result is for the overall search, but if you were to take into account the different regions of parameter space, higher mass signals, much shorter, are often hard to distinguish from the background than longer signals, because for a longer signal, you need to match a template over a whole wide range of frequencies over a long time interval. Short signal, you just need a short burst of noise to match, so glitches are much easily confused. Our false alarm rate calculation takes that into account, but it means that at a given false alarm rate, you can get different detectability. So different sources are detected with different efficiency, which means that if you see, say, 10 systems at one mass and 5 at another, that doesn't necessarily mean that the ratio is 2 to 1 between those two masses if you're much more efficient at detecting one mass range to the other. So we need to subtract out our selection effects to go from our observed population to the intrinsic population, and that's part of what's going on here. Got a question here. Does the prior depend on the template waveform? Note that the prior just depends on the physical assumptions that we go on. So say a uniform distribution of masses would be one example. The template we can calculate wherever we like within that region. Sometimes we will impose prior boundaries because of the template, in the sense of we know that templates can't be calculated outside a given particular range of parameters. So for example, for a mass ratio more extreme than 1/20, the templates don't work particularly well. So we might impose a prior that says the mass ratio needs to be more equal than that. But that's more for ease of computation than an explicit dependence on the template. Does that make sense? Always tell me if things don't make sense. It's okay to ask a follow-up question. Okay, so we have the idea that we want to go from our observed population to our astrophysical population. So we want to divide out selection effects. The other thing we want to do is try and reconstruct the distribution. So we want to go from our discrete number of observations to understand what the population is. And so the way we do this within Ligo, Virgo, Kagura is we try not to make too many assumptions about the astrophysics of what's going on, but instead say, let's make some kind of parametric model that describes what's going on. And then we can infer the properties of this parametric model given our observations. So in this plot here, we have results using our third gravitational wave catalogue and using 4 different parametric models to try and reconstruct this mass distribution. In all cases, we're correcting for selection effects. We're using the same data. So, you'd think they give similar results, and the differences come in from the way they are parameterized, different ways of parameterizing the model. So the different models, one, binned Gaussian process. So here we're binning up the mass distribution. We're just saying there should be a degree of continuity between different bins, so we don't have wild fluctuations all over the place, but we say there should be different bins for different masses, and we're inferring the heights of these different bins when we fit to the data. So you can see this jagged line here traces out the outline of bins. It's not exactly flat because the bins are defined in chirp mass space, I think, rather than M1 space, and there's a kind of transformation you need to do there. But you get this binned distribution that traces out the number of astrophysical sources in different ranges. Okay, the orange model is a flexible mixtures of Gaussian kernels. So we use we place down a different number of Gaussians at different points in parameter space and determine where these should be in the widths of them by fitting the data. Okay, so well, the bins will give you a jagged edge. The Gaussian kernels will always give you something smooth and smeared out. Potentially this could miss sharp features which the bins can pick up on, but it will also smear out perhaps some artificial discontinuities in the bin line, so that's quite nice. Now, there's all sorts of flexibility that we could fit with this. If we pick something, that should be, I'll need to correct that, that's typo, that should be spline here. Another thing we can do is say that, okay, we guess that the general shape of the distribution should be some kind of power law. Power laws we know are quite common in astrophysics. The initial mass function of stars forming is well modeled by a power law. So it kind of makes sense that when you look at the black holes at the end, that should be something like a power law. But because we know there's all this different physics that goes into forming black holes, the various mass loss rates, the different types of supernova, we expect there's some complexities on top of this. So in this model, we try and fit a power law or variable slope and a spline model that models deviations from this power law. So again, there's quite a bit of flexibility in this model to fit different things. The final model is perhaps the most rigid, but has been used a bit more in the past, is a power law plus a Gaussian peak. The idea here is that we'll say, okay, power law should be able to model to first order the mass distribution of black holes. As we know, it's something like the initial mass function of stars, or even if it was primordial black holes, power law is not a bad approximation over some scale. But let's add in a Gaussian bump at some point where you can move about where the Gaussian is, its height and its width and so on. And this would be a nice approximation because we might expect there to be a pileup at certain masses, say, for example, due to pulsational pair instability supernova. We know that those will shed lots of mass until they're all about in the same regime, and then we get an extra pileup there. So that's the least flexible model, but let's see what we come up with these days. Should also add each of these last two has some tapers on at high and low masses to taper things away. So power law plus peak, we're constrained to have a slope and an extra bump, and we can see that this bump is around about 35 solar masses at its peak, which is coincidentally where we would expect the pileup from pulsational pair instability to be. It's not enough to say that this is the pulsational pair instability bump, but it is in the right place, so it's consistent with that interpretation. And we can see that each of the other models also has a bump round about this point, varying width. So it looks like in the binned model, it picks up a bit of extra power at lower masses as well. It extends up here, so maybe it's not quite as symmetric as a Gaussian might assume, but from the spline, which is very flexible, we certainly have another peak here, and the kernels, Gaussian kernels, something similar. Maybe not too surprising that the Gaussian kernels looks like a Gaussian peak, but that certainly looks like there's a feature here. Have a general slope of masses, more low mass black holes than high mass black holes. That's good, because we know there are more low mass stars than high mass stars, so one would expect more low mass black holes than high mass black holes. Looking at lower masses, it looks like we have a peak here over about 10 solar masses and then a dip. Like, this dip doesn't show up in the power law plus peak Gaussian because it can't have a peak dip here. It's just a power law with something added on, so no way of having a dip. The other model is a bit more flexible. Okay, so we have some nice phenomenology. We see that our results depend on the model we use, but we can see similar features from it. So what are we really doing in this analysis? Well, we know we need to correct for selection effects, but what we're really doing now is another example of an inference.
Christopher, one question.
Yes.
So in the spline model, is there an understanding of the other peaks? Let's say the one bit at around 20 solar masses, I think. Yeah, just after 20. And if it's, and is it, sort of driven by some specific set of events, or is it like a robust feature? I mean, for instance, is there something like a leave one out analysis which is done so that, to establish the significance of that peak?
Yeah, so there are some checks. If you look in this catalog, so companion paper, there are some checks of it. So it's not just one event that's doing this. It really seems to be driven by a lack of events in this mass range, which you would expect. There seem to be a few missing there. What is less clear? So I think given the data, it seems to work out quite robustly that this is the case. This is what's going on. What is less clear is how significant that is in terms of this is just seeing one realization of the universe. We've only observed for a given amount of time, so we expect that the distribution of events we're seeing is maybe not exactly mirroring the true underlying distribution because it's just some realization of that. So it's a little harder to estimate that in what's going on, yeah, it certainly looks like, given the data, this is a robust feature. Given the population is a little more uncertain, and that really just comes down to the fact that we don't know exactly what the shape being fit is.
Okay, thanks.
Hi, I also have a question. So right now, say we are using a power law for these rates, but say when we get sensitive to lower frequencies and start detecting masses much higher than 100, right? Then do you still like see these models working? Because it would go down. Say you expect the PS and mass gap to not be populated, but then you expect that due to like sensitive detectors at lower frequencies, you will also have higher mass events. So would these models still work for those?
Okay, that's a good question. And I think there are numbers of different levels to this. So first up, as we go to higher masses, as go to lower frequency sensitivity improves, we go to higher masses and we should be able to detect higher mass systems than we currently can. That real difference will improve things at this end, but it's really at the much higher masses than this that makes the big difference. We can detect systems up here already, and the fact that we are not detecting them implies something about their number. So the fact that this trails off quite considerably is really down to the fact that we're not seeing those, even though we could detect them. However, as you're saying, maybe we have the pair instability supernova mass gap around here. We'd actually expect it to kick in this regime. So the fact that we are seeing things in it seems to imply that there's something extra filling this gap. But maybe we've just got it wrong, and maybe it's at higher masses. Maybe there are other things going on. It is certainly the case that each of these parameterizations is maybe not the best if we had a distinct population at higher masses. The binned model should be able to take care of this okay, because you should be able to go down and go back up again. You might want to adjust the priors on how much variation it can have between bins. Similarly, the flexible model should be able to take care of that if you allow a suitable weighting to add in sort of an extra cluster at higher masses. Power law plus spline is going to struggle with it if there's a gap, because you need a big deviation and then going back up. And if it's not the same power law above and below, that really doesn't add in the next thing, the right level of detail. And the power law plus peak is really not going to do a good job of it, because it's just one power law. So maybe a broken power law would be or adding in an extra component with a different amplitude. There's some suggestions for things like this done in the literature, but you would want some extra models there. Does that make sense?
Thanks. That does. Thanks a lot.
Okay, so there's a question about the upper limit on the core collapse supernova gap. I'm going to leave that question if that's okay, because we're going to come back to talk about this in the final lecture. And I think that would be a good time to talk about it. And I really want to make sure we can finish up talking about some ideas behind population inference at this point, if that's okay. So if I can ask you to hold on to that question, and if I don't come back to it in the final lecture, can you please make sure to ask again? Thank you. Okay, so yes, so I want to go back. What are we really doing for these population inferences? We know the basic ingredients. We need to take the number of things we've observed, take into account selection effects, fit some kind of parametric model to it. What in practice we are doing is another example of inference. So we're doing another time. Oh, I've lost my piece of paper. Ah, yes. Another application really of Bayes' theorem. So in this case, though, instead of given one particular structure of data and inferring the properties of one source, what we are doing is inferring probability of some model parameters, lambda, given a set of detections. Okay. Now these model parameters could be the bin heights in the binned model, could be the functional form for the spline, plus the power law slope. It could be the height and width of the Gaussian and the power law plus peak model. It's these particular parameters that describe the model in question, given the set of detections. So again, we do this as an inference. It's a probability of getting this particular realization of the data given our model of likelihood here times our prior on the assumed hyper model parameters. So these are often called hyperparameters because we're one level up of inference from these, and probability then of getting this complete data set. So in the next lecture, we're going to talk about how we calculate this in particular. There's quite a lot of mathematics to go into how to do this. So we'll go through this next time. I expect it will take most of the lecture to go through this. So a bit of warning that we're going to spend some time going through these different terms. The prior is perhaps the most simple. We can define a uniform distribution over, say, the height of the power law. This likelihood is a bit of a complicated term, okay, but it will be derived based on the masses from this stage here. So we'll see how we take the posterior distribution from this level and move up to this level here. So we'll take a look at that next time. But what we're really doing is inferring probability distributions over a set of model parameters given our observations. Then we take those model parameters, put them back into the models we have, and we use those to define these curves here. Okay, and that's the level of inference we get coming out of these systems here. Okay, so one thing I want to point out coming back from this point, having now inferred the astrophysical distribution, we can use this to look again at other results we have calculated. So what I'm showing here is results from a rather nice study that shows the posterior probability distributions on chi-effective for the events back from our first catalogue of gravitational wave detections. So these plots, called Violin Plots, the width of the distribution shows the probability distribution. So higher probability where there's further away from the line. And what we have is that the standard priors, the priors that we use in our standard Ligo, Virgo, Kagura analysis, are shown by these colored lines. Okay. So these are the probability distributions that you would look for and find if you looked up in our catalog papers. The various curves here. What is shown in the white curves is what happens if we change our prior. So if we go back and swap out this prior, the one that we used in our original Ligo, Virgo, Kagura analysis that was quite uninformative, and replace it with a prior that we think represents the population given all the other observations. Okay, so it's a population weighted prior. And you'll see that this does have an impact on the results. For some events, this is a very small impact. So for 150914, you see there's very little difference between the left and the right side here. This is quite a loud event, so the prior is less important. The likelihood dominates the posterior calculation. Some quieter events like 151012, you see it narrows the distribution somewhat. We add in the information from the other events, that gives us a bit more confidence. It reduces the overall uncertainty, so it tightens up the distribution. For 170729, this is the most notable difference. With our standard priors, just considering our event on its own, we can infer quite a high chi-effective. Now this is unusual. So given the population of other systems, we're basically saying that given what we know of the other events, which mostly have chi-effective round about 0, we're more inclined to believe that this has a lower chi-effective. We still have the likelihood that pulls us up to higher values, but balancing probability, we think actually it's more likely that it's like the other events, and we just have a noise fluctuation that happens to take us to look like we have higher chi-effective. So this pulls us down to be more consistent. So this is a rather nice example of why considering the population is important. It can give us a more detailed understanding of all our events. And in particular, when you're looking at outliers, it's always good to reinterpret them in the context of the population. Right? If you have 100 events, it's not too surprising if one of them is a 1 in 100 fluctuation. We have some unlucky noise fluctuation. That makes it look really weird. So it's always good to try and put things into the context of the population and see how that impacts things. Now, a caveat to doing this is that you need to have a population model that will work across the whole parameter space. So this actually connects quite nicely to this question of, will it work when we continue to get higher mass systems? If we had, a 200 solar mass system and all our models end at 100 solar masses, then doing a population reweighting will give us, would definitely pull down the mass to make it consistent with everything else. But that might just be an artifact of our model, that the model doesn't describe this very well. So population priors are a nice thing to do to check the consistency of results, add in the information from everything you're seeing when looking at individual systems. And we know we should always be careful when looking at the properties of individual events. However, you must also check that your model is working properly, that you can describe the full diversity of the events you're seeing. So you need to be careful with what's going on here. An alternative to using one of these population priors from a parametric model is to say, well, why don't we use a particular simulation? Why don't we say, let's assume we have things formed from isolated evolution. Then we have a prior expectation of what the mass distribution should be like, and we can use that as a prior distribution instead. That is also possible. There's some studies of this. Here's one which I was involved in, where you can use these and map the properties of the source. The caveat there is, of course, we know we are uncertain on our source properties and also the channels involved. So actually doing the proper analysis of including channels and variation of channels is very complicated. And we can't use it as a prior in the same way as if we want to then constrain the model parameters. So that's quite complicated, but it is also a thing we can do. Okay, a question here. A violin, what is the two sides? Okay, oh sorry, I obviously didn't explain this quite well enough. The shaded side is the result, the distribution you get with our standard Ligo Virgo Kagura prior. The white side is what you get with the population informed prior. Okay, so the blue results is what you get if you just loaded up our Ligo Virgo Kagura results. The white here is what you get after weighting by the inferred population distribution. So this adds in the extra information from all the other events. So this is what happens when you change your prior distribution. It influences the importance of the prior distribution and highlights that when looking at outliers, that might just be a particular noise realization, which is unlucky. And when you add in the population inference information, you're more robust against that because that takes into account the probability that you have one amongst your population that's a fluctuation here. Okay, does that make a bit more sense?
Hello. Yeah. Thank you.
Okay. So recapping, yeah, where are we? Going back to our big questions. We've spoken about how to detect a signal. We know that we want to calculate the false alarm rate. We need to do this empirically. We search for signals. We look for outliers, calculate how frequent such things would happen if we only have noise. And then we can also combine that when we have some knowledge of the population with the true alarm rate to calculate the probability of it being a real signal. If we want then to go, okay, we've got a signal, what are the properties of the source? We do parameter estimation, we do some Bayesian inference, we take templates, we match to our data, and we get probability distributions from the source parameters. These do depend on our templates being accurate and also depend on the prior that we assume for the source parameters. In our standard analysis, we try and pick uninformative priors, which are then easy to use in subsequent analysis, but they're not necessarily the most realistic. Okay, given our estimates for source parameters, subject to the assumptions that we've made, we could then look at the population, correct for selection effects, and try and figure out what the underlying distribution of sources is. For this, we typically use parameterized models within Ligo Virgo Kagura rather than trying to fit particular simulations. But given that, that gives us some understanding of the shape of the source distribution. And then given this knowledge of the source distribution, we can propagate this backwards to calculate the true alarm rate for our P-astro calculation to determine do we really have signals or not. And we can also reweight our parameter estimates with a more realistic prior, hopefully factoring in the rest of the observations to get a better understanding of our source parameters. In each of these stages, there are some assumptions that we need to be careful of. We need to watch out for that our noise is nice and Gaussian for parameter estimation. We need to be careful of glitches. We need to be careful that we're not over-interpreting things which are an impact of our prior choice on the source. For our population inference, we equally have to be careful that our model is accurate enough. That is, we're not overfitting the data and fitting fluctuations which are just random result of the realization of the universe we have, and that it works over all ranges of parameter space, that we're allowing the right balance of flexibility to fit all these features. Okay, I think that's all I wanted to say for today. Do we have any more questions?
So yeah, I had one question on, so I mean, non-Gaussianities, glitches and stuff like that move just by, sort of methods like this. But what about non-stationarity? I mean, do you expect that this will become important for analysis of, say, long signals in future detectors?
Excellent question, yes. So non-stationarity, for those who've not come across this before, is this idea that our noise curve here, giving the average properties of noise in our detector, can vary with time. Things change in our detectors, things drift with time. So our noise curve at one time is not necessarily exactly the same as the noise curve in another time. So in our searches, we actually track this. We recalculate the noise curve as we go on. We can add in some drift with time to try and calculate these noise fluctuations as part of detection. And in parameter estimation, what we typically do is calculate the power spectral density of the particular stretch of data that we have. Now, when we're doing searches, we're looking over long stretches of data, looking for many signals. So we know that the variation is important. For parameter estimation, we're typically looking at just a few seconds. So we generally approximate that any changes in time are quite small because we're only looking at a short time. However, when we improve the sensitivity of our detectors, we can see signals for longer because we're going down to longer frequencies. This approximation may start to break down. So yeah, we might need to worry about this, particularly for third generation detectors. How significant that will be will depend on the detector performance. So I don't know we can say for certain how big that will be. There is some work, I think Colin Talbot was first author on this, with Eric Thrain, looking at some ways of adding in some time variation into our parameter estimation analysis. So there are some things you can do to take into account some drift here. So yeah, this might be something that definitely needs to be looked at for third generation detectors. Whether or not it's important for second generation, I'm yet to be convinced either way. So it might be something to worry about. Might be a good thing to study in more detail as we look at future observing ones. But for most of our analysis so far, it should be fairly safe.
Hello. I had a question about, so do we have any simulation codes where one can simulate, let's say, multiple formation channels simultaneously?
Yes, good question. I think the answer is no. We have no code that will allow you to do the simulations for multiple channels. Well, modulo the fact that, so depending on what you call different channels. So we have codes that can do isolated evolution. So they will be able to do common envelopes, stable mass transfer, chemically homogeneous evolution. They'll be able to do those together, but wouldn't be able to add in globular clusters, nuclear star clusters, primordial black holes. So yeah, there's nothing that will simulate those. There are some codes which are compatible with each other, so that you can set up isolated evolution and say globular cluster evolution to be consistent with each other. So there's code Cosmic, which I've shown some results for in previous plots in last lecture, which is good for isolated evolution. And this has been incorporated into the globular cluster code called CMC. So the stars that are involved in their globular cluster simulations are involved using Cosmic. So you can set up a Cosmic simulation of isolated evolution and a CMC simulation of globular clusters with the same comparable set of calculations to get consistent results. But I don't believe there's any particular piece of code where you can say, give me everything all at once, all consistent. Yeah.
I had just one more question. So we saw that none of the population, this simulations predict very low mass ratios, like less than 0.4. But we have already seen a couple of them in the Ligo Virgo. So is there any explanation for that?
That's an excellent question. Yeah, currently the most extreme mass ratios are extremely difficult to explain via any formation channel. There may be some channels which can predict them, but not in the numbers consistent with what we've seen. So I think this is currently uncertain. There are things you can do by allowing more accretion. So if you allow much higher accretion rates, you can, in isolated evolution, you can get some more extreme mass ratios. And there are also some predictions in the AGN channel where there are more extreme mass ratios. But yeah, I think this is certainly one of the current hot topics of trying to see how the models could be improved in order to take these into account.
Thanks. Yeah.
I have one more question. It's a follow-up on this same topic of non-stationality. So if the SNR is too high, let's say the event is very loud, then do we still have to worry about the noise? I mean, the dynamical noise, do we still have to worry about it?
Okay, that's a good question. So yeah, in the very high signal to noise ratio limit, you become the noise becomes less and less important is basically the answer. So yeah, the accurate modeling of the noise is comparatively less important, so you don't need to worry about it as much. There are some other things which you might need to worry about, just the performance of the detector for very high signal to noise ratio signals. But yeah, the noise becomes less important as the signal to noise ratio goes up.
Oh, thank you.
Hello. So I have a follow-up question on the formation channel thing. Like you showed the Violin plots for chi effective, and most of them were consistent with 0, right? And does it tell us anything about the formation channel? Like, have some of them been ruled out because such, say, telltale signature, which I shouldn't be using because there's so much of degeneracy between the channels, but still, do we know anything about their formation channels?
Yeah, so it's a good question. And I think we'll come on to this a bit more in the final lecture. But briefly, yes. So if you remember some of the predictions that we have for what chi-effective should look like here from different channels. So large chi-effective would be expected for chemically homogeneous evolution and for isolated channels, so stable mass transfer, common envelope, if black holes are born with large spins. So the difficulty with having chi-effective close to 0 is that it could be that you have a dynamical formation, so you don't have aligned spins, or it could be that your spin magnitudes are just small and you can't necessarily tell those apart. So if you had a large chi-effective, it would be easier to rule things out because you wouldn't expect dynamical formation if there's large chi-effective. But when chi-effective is close to 0, you have this degeneracy between spins are small and spins are all over the place. So it's a little difficult from that point of view. And the second point is, in general, we expect there to be a mixture of the different channels. So we can't necessarily rule things out, but we can just say, okay, the majority of binaries are not formed by chemically homogeneous evolution. So that doesn't necessarily mean that there's not a small subpopulation that are formed. So ruling out quite difficult, putting constraints on is more possible.
Thanks a lot.
Okay, and we'll come back to this in the last lecture. So I think any follow-up questions on the population, we'll come back to those later.
Do we have any final questions for the evening? So I'm seeing a very satisfied silence here. So I think we can conclude the lecture today. Many thanks to Christopher again. We'll reconvene tomorrow afternoon for the next lecture in this course. Thank you, everyone.
There's one more question in the chat I'd just like to take. Does SNR in the signal slow down the PE process, or does it speed things up? There's a bit of a balance. If you're very quiet, the PE can be really difficult because it's hard to find the signal. So that's a problem. When you're very high, that also makes things difficult because it's a very sharp likelihood to find. So both extremes are bad. We're quite happy for signals which, 10, 20, well, 10 would be a bit low. SNR 20, that's quite nice. Getting higher than that causes problems. Getting lower causes problems. Generally want to be in the middle.